Welcome to your future. Welcome to Vision Academy. Let us unlock your full potential.
Look at this equation for the combustion of propane. C3H8 plus O2 yields CO2 and water. As written, this equation is physically impossible. If you track the atoms from left to right, carbon goes missing, and oxygen miraculously multiplies out of thin air. That imbalance violates the law of conservation of mass. In a chemical reaction, matter cannot be created or destroyed. Every single atom that goes into the reaction must come out the other side. To align our math with that reality, we adjust the quantities. We do this by adding coefficients, large numbers placed at the very front of the molecules to act as multipliers. But there is a strict rule you can never break. You can only add coefficients to the empty space at the front. You can never touch the small subscripts locked inside the formula. Changing a coefficient just gives you more of the exact same substance. Changing a subscript alters the physical identity of the molecule itself. To fix this equation without making a mess, we need a baseline inventory. This chart splits the reactants on the left from the products on the right, so we can track our carbon, hydrogen, and oxygen. On the left side, we read the skeletal equation exactly as it stands. We are starting with 3 carbon atoms, 8 hydrogen atoms, and 2 oxygen atoms. Moving to the right, we do the exact same thing. We have 1 carbon atom, 2 hydrogen atoms, and 3 oxygen atoms, noting that the oxygen is split between 2 different products. Comparing the 2 columns makes the problem obvious. Our carbons drop from 3 to 1, our hydrogens drop from 8 to 2, and our oxygens jump from 2 to 3. This complete, accurate starting inventory is non-negotiable. Skipping this step usually leads to compounding mathematical errors when we apply the hit and trial method. Step 1 is targeting the primary element. We start with the element that appears in the fewest compounds, which right now is carbon. To get our right side to match our left side, we need 3 carbons. So we place a coefficient of 3 in front of the CO2 molecule. That 3 immediately multiplies the carbon attached to it, bringing our right side carbon tally up to 3. However, that coefficient applies to the entire molecule. It also multiplies the 2 oxygen atoms attached to the carbon, giving us 6 oxygen atoms from the CO2. We then add that 6 to the single oxygen atom still sitting in the H2O molecule, updating our right side running total to 7. Balancing one element automatically disrupts another. It is an iterative process, which is why we must take it step by step. To avoid getting trapped in an endless loop of changing numbers, we follow a strict sequence. We leave oxygen and hydrogen for last, and between those two, we always handle hydrogen first. We have 8 hydrogens on the left and 2 on the right. To turn 2 into 8, we need a multiplier of 4, so we drop a 4 in front of the H2O molecule. That coefficient multiplies the 2 hydrogens, bringing our right side tally up to a perfect 8. It also multiplies the single attached oxygen atom by 4. When we add those 4 oxygens to the 6 we already have from the CO2, our new right side oxygen total becomes 10. Because hydrogen and oxygen frequently appear in multiple compounds across a single equation, saving them for the end keeps our earlier work from unraveling. Now we address our final imbalanced element. Our right side is locked in with 10 oxygens, and our left side currently has 2. We need to find the multiplier that turns 2 into 10. That gives us a coefficient of 5 to place in front of the O2 molecule. Multiplying out that new coefficient brings our left side oxygen tally up to the target of 10. Looking at our inventory columns side by side, we can confirm the math. 3 carbons, 8 hydrogens, and 10 oxygens on both sides of the reaction. Before we finish, we perform one final check on our active coefficients: 1, 5, 3, and 4. These numbers are in their simplest whole number ratio, meaning they cannot be mathematically reduced any further. The numbers on the page now accurately reflect the physical reality of the reaction. We have completely satisfied the law of conservation of mass. Starting from an impossible imbalance, the hit and trial method successfully mapped out the exact quantities required to execute this reaction. This straightforward approach works perfectly for standard combustion and simple molecular reactions. If you encounter highly complex redox reactions or ionic equations, you will need to scale up to algebraic or half-reaction methods. But for the vast majority of introductory problems, this 5-step checklist is all you need. Take an inventory, lock the subscripts, balance the primary element, fix the hydrogen, and finish with oxygen. By applying this method, abstract letters and numbers stop being a puzzle and become a precise map of how the physical universe actually operates.
Like this video? Subscribe to our channel. Share this video. Thank you. Shukriya.